Okay, sir.
Apologies again for my noisy background. So yeah, we are 8 people over here. So till others join, I would like to propose, if you have any doubt or any topic needs to be covered, you can suggest now. If you want to ask anything related to 3D printing as such, we can utilize some time to have a discussion. Okay, all right. So since last time we discussed, we wanted to know some a bit about reverse engineering. We'll take a look into that, and certain imaging techniques will be the second part of this lecture. Sorry, perhaps the first part of this lecture will be some imaging techniques, and then the reverse engineering part. That will make much more sense. In the third part, we will look into some advanced 3D manufacturing processes that might open up the possibility of research scope among your peer group. Okay, so I'll share the screen. We can get it started. Do give me a voice cue if you can see the screen clearly.
Yes, sir.
Okay, great. So to understand what's behind reverse engineering, I mean, the word itself suggests that already something has been engineered. We are only going to learn from it and make a utility-based product by our own. So to cater that uh, and notion of reverse engineering, we need to understand something called as the scanning part that works on the backdrop, but is equally very important considering the technical aspects from an engineering perspective. Right. So the scanning and reverse engineering go hand in hand. So I have put here examples, two examples, where scanning is effective, and from that information, the recreation is done. So as you can see, towards your left is actually a pipe inspection robot. Okay, so which is mounted with some infrared sensors and RGB cameras. Okay, so it goes into the pipeline, and as it travels forward, it scans the entire surface texture of the pipe, which implies that as we get the information of the interior of the pipe, certain defects and or certain manufacturing limitations might be very well understood from this particular information. On the right, what you have is a 3D scanned part, uh, from which we can recollect some information of damage or of fracture, of strain, of thermal stresses being developed. Okay, so this surface-based information is very important because that goes to show in prediction that how certain non-destructive testing methods can be applied so that we can get accurate representation of the process parameters. Okay, right. So as you will realize that any non-destructive system, or not any, maybe the optical based system is one of the non-destructive systems that we can bring into place. And as well, this optic system is the fundamental element through which the reverse engineer product are being built. Okay, so let's look into this picture. Can anybody tell me what is it? Give me a voice cue.
Sir, MRI machine.
Yes, that's an MRI machine. Anybody with the full form? Magnetic resonance imaging. And what is the picture on the right? What do you call it as? Any idea? Has anyone been into this? Do you have your brain scanned like that? It is called CT scan, right? CT scan or computer assisted tomographic scan. Okay, so this sort of information is very vital for people who are involved in surgeries. I mentioned people and not doctors in specific because it has also been an interest of engineering discipline very recently. Why? Because these scans only give you a superficial representation. However, if in some way you can use this scan to regenerate the brain, then the doctors, of course, or the surgeons can carry out the surgery on a hypothetical model of the brain itself and then see what sort of challenges may arrive prior to the actual surgery. So this gives a tremendous technological advantage so that uh, we can do benefit to humankind. And this is only possible because of one, the scanning system, two, 3D printing, because we are able to create some solid models out of it. All right, so we will move forward with this information. So how does the detection system work actually? Okay, I believe you must have heard about. Okay, I cannot get this pointer working. Sorry. Can you see the pointer?
So,
I can't see my pointer.
Yes, Yuan, it's not visible.
Right. Wait, just.
Now it's moving a little bit.
Okay, I believe it just up to the slide there. Okay, yeah, I think it is there now.
Yes.
Okay, so what we do here is that, say in a CT scan machine, we send a beam of X-rays. Okay, there's a array of X-ray emission tubes through which the beams travel. Okay, and we have a similar array of detectors now, which capture this X-rays midair. Suppose now, if I try to detect what intensity is arriving at the detectors, I'll get 100% intensity, and maybe because of some interference from each beam, the intensities might vary slightly. So if we calibrate each emitter, amplitude signal of each emitter, this part is called calibration. Okay, calibrate so that each detector now has 100% of intensity. Okay, so once we have calibrated ourselves in free space, so if we put up any random object, say for example something like this, what will happen is there will be some sort of signal attenuation, which means that the beam which is passing through this particular part will lose the intensity as it falls into the detector. So slowly and gradually, what we see is that the density of detected beam gently reduces, okay, as per the object. All right, now the thing is that it is only going to give me a profile like this maybe. Okay, so this is percentage of attenuated signal. Okay, and this is simply length of the array beam. All right, now the idea is to rotate this entire system by a full 360-degree circle. Okay, full 360-degree. So what we will get is the profile for each theta, isn't it? Theta being the angle of rotation. For each theta, there will be a different profile. And if we further superimpose them sequentially, then what we will end up is with is the exact representation of the image. So let's take a look at if the theta value is equal to 0. I just shoot the beam. So what I'm going to get is a first angle line like this. Then I rotate it by 90 degrees. So as you can see, two layers of beam are getting interfered among each other, isn't it? Okay. Still, it is not representing the exact image that we are looking after. Now again over here, as you can see, some 8 angles are being included. I mean, the capture is being done with 8 angles and superposition of these beams have been done. So as you can see, barely the surface texture arises. Okay, and eventually with 45 angles of capture, this intensity profile is built up. And thereby you get the 3D scan with 180-degree angles, which implies that if you capture the beams at significant resolution, you can easily recreate the image. But then it will be slice by slice, one layer at a time. So if you look into the magnetic resonance imaging machine, which has a different principle of operation, of course, but the CT scan is same. The patient has to slide in and out of the system, which means that to capture a 3D projection across the height direction, this 2D scans are then represented, and hence whenever we look at our CT scan images, there are plenty of them across the table, looking at which the idea of defects can be pointed out. Okay, is this part clear? Just let me know how this scan system works.
Yes, sir.
Yes, sir.
Okay, great. Right. Now, the thing is that, as you can see, you will see a sort of a umbra penumbra sort of a system, okay, where there is a diffusion of light across the surface. And it is because, if you remember, the interference of the beams from the detector to the from the emitter to the detector, okay, this interference causes this expansion of light, and hence exact recreation is a little impossible. Because of which, what we do is we go for a filtered back projection. If you recall, this entire process is called back projection, but to gain certain edge over the profiles, we go for something called as filtered back projection. A mathematical relationship has been provided here. I think this will not be of much relevance to you now. This is also part of the research work that I'm doing, and slowly you will see how these are now capable of, you know, reforming 3D printed objects. Okay, so this filtered back projection actually uses a Fourier transform. I hope if you have not even, covered Fourier transform now, you will soon. And that is a very essential tool in any engineering application. So what it does is that the Fourier transform, it suppresses the frequencies based upon their intensity. Okay, that is all that you need to know for now. So you use a Fourier transform, and then you put it into the back projection algorithm where superimposition of these beams occur, and thereby you get a good representation of the image. So with filtered back projection, as you can see, the sharpness of the image is very discrete now. Okay, you can compare it between the upper row. All right, I hope it is clear. So these are sort of algorithms where a lot of work needs to be done, because as you can see, if I would have had a hole in between, would this filter back projection work? Okay, those are some interesting research concepts. So what we are looking at is the simplest form of it. So this process of taking the projection is actually called RADON transform. Okay, so Fourier transform and to that extent, if you relate it, it's called a radon transform. So the idea is, if I have an object, I pass a beam of light, I'll get some projection, and I'll take the summation of this projection, integration of this projection, to form the image. So here is another example to, further, clarify the concept of this back projection technique. So the first element is take a radon transform and then apply the back projection. Of what kind? Filtered. Okay, so what you get is a 2D slice of the 3D object. Okay, an interesting case over here, what we have, two dots. So as you can see, if I have my theta angle at 0, for this particular circle, I'm going to get a nice peak. For theta equal to 90, say I'm capturing it from here and then from here, what I'm going to get is another peak. That is obvious. But if I capture, say my theta angle is 0 over here, this particular angle I'm trying to capture, so I'm going to get two peaks, isn't it? One is a little grayish than the other, so I'm going to get two peaks. But if you capture it from over here, what you'll end up is the superposition of the intensities. So as you can see, the recreation of image is not really very easy when you are considering such propagation techniques, which also translates to the fact that you also need some material which will not diffract the rays. Okay, anyway you are capturing the attenuation, but also diffracting will create further hazy pictures, which means that when you are reverse engineering any equipment, or say a medical uh, case, you have to clearly understand what you're beaming at. Okay, and the materials that are involved should not have a property that distorts the image, or even if it does, you have certain algorithms that rectifies it. Okay, so that's a recreation. As you can see, the radon transform and back filter projection leads to some hazy pictures of two dots over here. Okay, so one standard test to accurately see how well your algorithm is working is to implement this SHEPP-LOGAN phantom image. Okay, so that's an image. If you take radon transform and back projection, it sort of relates to the brain also. So this particular image is the most accepted standard for any 3D printing device, which means that we use it a lot of times to calibrate the machine, okay, of 3D scan systems. So as I was talking about the CT scan tomography, okay, computer assisted tomography. So this tomographic technique is now used to print 3D objects. How? Imagine, rather than beaming a section of X-ray, I'll do a beam using a DLP projection system, of course, a solid image of UV light onto a resin. Okay, and then I'll rotate the resin. So what will happen is the resin will get cured on a 3D coordinate system. Okay, so as you can see, there's a man sitting on a pedestal, and these projections of the images are being taken. Okay, so if I happen to shoot these rays of beams into the resin, what will happen? The curing of the resin will take place, and eventually you are going to get a 3D cutout system. All right, as you can see, that's a image number 1 with only resin, image number 2 with one angle of projection, image number 3 with two angle of projection, and 4 with 36-degree angle of projection, and eventually the within the resin the body has solidified of the man sitting over here. Okay, so can you guess what will be the time taken to 3D print this object? Any guesses over here? You can type it in the chat box. Any guess the time taken to print this object? Less than 1 hour. Okay, great. Few hours. Few hours is a standard FDM process. Okay, few hours is a standard SLA process. So this particular technique, which started at MIT in 2017. Okay, now in 2020, prints in 35 seconds, and that is a game changer. Okay, you are printing any 3D printed object in 35 seconds. Okay, why am I talking about any? Because it doesn't matter uh, within this resin size, of course, it doesn't matter how many components are there. Everything is getting printed in one single projection. Okay, so this is revolutionary, and I wanted you to know it because it is very latest. All right. The benefit of this particular invention is that if I place a metal in this container of resin, if I place a metal screw, okay, not a metal screw, say the tip of a screw, okay, I can print the handle on top of it. Now, this was impossible using any for previous 3D printed printing techniques. Okay, I can print a handle on top of it, which means that it allows in object printing also. So this was the most simplest example, which there are certain papers, of course, this was, I believe this is from UCLA. So in this paper, they describe how this printing is carried out, how backpropagation filtering techniques are being taken into account. So multiple disciplines of engineering have come together to develop this 3D printing object, and then they are achieving accuracies up to 500 micrometers. Okay, so you're getting 500 micrometers of accuracy in 35 seconds, which means that now the organs, critical organs, with just one scan can be 3D printed, and the doctor can look at it right away with this particular machine. So this is a breakthrough in 3D printing, and I wanted you to know, but without certain imaging background, this wouldn't have been possible. Okay, so how do you imagine the machine? Very complicated, very tedious? Actually, no. It's just a simple projector with a DLP chip. I'm sure you are comfortable with what's a DLP chip, and a resin with a rotating mount. Okay, it's just that another projector is placed at the bottom of it. Okay, so as you can see, the images, the object that is being created, all right, in sequence to the angle of rotation. So they are successful in developing a full object in almost 290 rotations. Well, of course, with 360 you get perfection. Okay, but 290 was sufficient enough to make this ballet dancer. Okay, the challenge here is the material. Okay, the amount of oxygen concentration, the amount of inhibitors in the resin has to be controlled precisely. That's the only downside, which of course allows for much more research scope. So you can think about in civil engineering projects that you just beam an image of a house and it cures, the resin cures, so you drain out the resin, whatever is left. Okay, so instead of resin, if that can be done to concrete, so that's a wavelength kind of a decision, at what wavelength should you beam the entire image. So this method can be realized in n number of printing cases and will have significant impact in the industry. Okay, so that was part one. Any questions from this part, from tomographic 3D printing? Okay, seems we have none. I hope you are getting it. Am I going too fast? Okay, all right. So we'll proceed with the second part of the presentation. Right, so this is 3D systems. I forgot to include the name. Geomagic. plus capture hardware. Okay, this is available in AEC, the 3D printing, 3D scanning system. As you can see, it has a camera, it has a podium, and this is the part that you want to reverse engineer. So you're already now exposed to one of the imaging techniques which can be recreated to a 3D printing mode. Okay, but we will look into these different modes where you want to go through a solid model before getting the part printed. Okay, so the USP, it captures 1 million points, data points, in 0.3 seconds. So an exposure time of 0.3 seconds, less than the time taken to blink an eye. Okay, and it captures 1 million points. So in 1 million points you should have the accurate resolution, but then again for some parts you have to move this object in a very calibrated fashion. Okay, by the way, this is a desktop object, which means that there's a computer and there's a small pod like system with a camera stand. Okay, so how does this system work? So it has a projector that projects a particular wavelength of light, and the camera that detects the bending of light. Okay, and this bending of light is can be detected by two cameras, just like we have two eyes for depth perception. So similarly, if you get two cameras looking at an object, it is going to give you a depth perception. So you get the 3D object, capture it from the two cameras merge the image to form one 3D layout of points. Okay, but this is not sufficient, because as you can see in this diagram,
Juan, you are not audible. Hello. Let me call him.
surgical elements. Did I lose connection?
Juan. Juan.
Yeah,
Hello.
did I lose connection?
Yes, you were lost.
Okay, okay, okay.
Maybe 1 minute back you have to connect.
Okay. So was I here or here?
Wait.
Can you see the screen?
Yes. No, you went
In
to
the
the
next
next
slide.
slide.
In the next slide. Okay. Thank you. Right. So did you get the working of this particular scanning system?
No, you were talking about it was not sufficient to capture the
Interior profile, right?
Yes.
Okay. Yes. So one, it has blind spots. Two, the interior profiles cannot be captured, unlike the topographic method. A tomographic method. The tomographic method captures the interior parts also. Now the thing is that we will see we have to recreate the geometry even after scanning to get the dimensions in a printable format. Okay, so that is again one thing. As you can see on the bottom, there are some resolutions mentioned. okay, and that at 300 So how does it change with the depth? Okay, so this is an important aspect. Say I place this 3D object very close to the system. So what am I going to get? The detail of the image is going to increase significantly, isn't it? But the field of view reduces, isn't it? The field of view reduces. Also, if I have large objects, I'll try to put these objects very further apart. In that case, I have a very high field of view. Field of view is high, but the resolution is low. Okay, this is exactly what's happening. As you can see, this is 0.11 mm at 300 mm and 0.08 mm at 157 mm. Okay, this is exactly what's happening with the system. So 3D systems provide this capture in two categories, capture and capture mini. So these are the resolutions which relate to capture and capture mini. It gets really significant because say you want a very high resolution of a certain surface, then you have to bring in the object up front, okay, to get the high resolution. Or otherwise, if the complexity of the part is not much, you can of course send it back to get a overall picture of the object. Okay, so once that's done, we can now take it to the software end. All right, yeah. Again, we have this particular case where you can have 3 cameras simultaneously capturing the data points. Okay, same concept, blue light capture, 2 cameras are capturing the information, the reflection of blue light, and then all the data points are stored. In this case, you don't have to rotate the orientation unless there is a blind spot. Okay, also in the demo of the 3D printing system, there were certain patches, stickers that are available in order to mark the boundaries of the volume that needs to be captured. Okay, these are very conveniently used and are detected well by the system. So if you place this stickers in any part of the object, it kind of also gets an idea that what the size of it is stored in the system, and it tries to compare that what's the difference in the geometrical diameter. And once it realizes that there is a difference, it easily captures the displacement. But it is not necessary or mandatory to put. That is when you are working with very critical systems. This sort of arrangement is best suited for a large-scale 3D scanning systems where a lot of scanning needs to be taken place. So in cases where we need to inspect, say, bearings, inspect electronic equipment for damage, or even inspect concrete. Okay, in these cases, this a conveyor belt will be set up over here where parts will move intermittently, and then you can capture readily in one go without any rotation. All right. Okay, so the softwares that come with it is the Geomagic Design X, Geomagic Control X, Geomagic Wrap. So these two are not available perhaps because I was not training them. I was given a demo of the Geomagic Design X. Okay, so we will continue. I have basically ripped off some important parameters of the Geomagic Design X from of course a YouTube video which is readily available for all, but a lot of tutorial videos are actually available with the computer itself. Okay, if you go to the sustainability lab, you will find a lot of tutorials within the software domain. Okay, and one can easily practice and see how they can recreate or re-engineer an object. Right. So if we have a part which is a little complex, which looks like this, so you will have these data points, okay, an image like this out of a scanning system. So with multiple projections, as you can see, there are different colors of yellow, pink, red. Yes? Anything? Yeah. Did I hear somebody speak? Any doubt?
No, no, you can continue.
Okay. All right. So as you can see, we have different colors that represents the different angles that have been used to capture the points. Okay. Each of these colors actually are the captures from different angles after rotating the image. So we need to provide an axis from which it should be able to relocate, that at about what angle you have relocated the body. So once you have superimposed by defining the axis and the points, the as you call it, the pivot points. Okay. Yeah. So once you have denoted that, say for example, for all the views, all different views, say you consider this circle as your pivot. Okay. This circle is your pivot. So what happens is that all the images will try to transform itself into this particular orientation and then superimpose. So what you get at the end is a complete reconstruction of the superficial information of the object. Okay, so that is step number 2. Often we need to capture multiple angles and repeat them so that we can get accurate representation of the surface profiles. But in cases of simple cubes, it is not mandatory. Okay, so here what we have is a regenerate option. As you can see, the sheer action of getting data points also takes into account the edges or the surface that has been written around the object, which might not be part of the geometry. Then again, this becomes very important when you are orienting the object. For example, say if you have a single cylinder which is standing on a flat plate, you want to recreate a geometry like this and you put it this way, chances are that the information between the surface on which this object is sitting and this particular surface will be lost. Okay, or maybe confused upon. There might be irregularities in this information. So a good way to do is that you better tilt the cylinder and create a non-uniform geometry, non-symmetric geometry based upon the axis of rotation, and then put it on the table. There you can easily, the software can easily discriminate between the positions. Okay, so if it does, you can quickly delete it from the object. As you can see, it has captured the surface and then it's gone over here. So that's a regenerate option which is available in the system. Okay. Right. So once we are done with this lump sum model, you can of course see that there are a lot of patches and there are some highlighted lines, okay, of yellows. So this actually represent the probable boundaries that the 3D system has conquered. Okay, so what we are going to do next is to actually model 3D model in and around the geometry, but the entire process of modeling will not be dimension based, but will be sort of prompted by the software. So as you can see over here, it had a central hole. Okay, there was a hole in between the object. So if you click on a circle, it straight away describes the circle without you needing to specify the diameter of it. Okay, it has by default prompted. Then again, if you try to select a circle, just like SolidWorks, there's a circle option over here. Just like SolidWorks or AutoCAD, if you select another circle, it will prompt that the outer surface is over here, and you don't need to have a continuous circle, so it will remove all these parts. Okay. Further, the outer texture profiles can be done similarly, and then what you do is simply extrude the system. While extruding the system, often the information about the holes gets lost. Okay, then you have to select the holes individually as they will be highlighted in the texture. Okay, and then go to extrude cut as you do it in a solid modeling software. So once you have done the extrude cut, all these geometrical surfaces will appear, which will be seemingly relevant to the actual model. Okay. Now, as you can see, we have certain information of this particular object where all the uh, information is being compared with the solid model that you have developed, and it has immediately detected that there should have been a certain surface information over here which is missing on the solid part. Then you can go ahead and simply make this holes. Okay, now the trick is, as you can see, this object is fairly being cut out very precisely. The 3D printing software prompts it that there is a fillet in this particular area. Switch the cursor position color. Okay, as you can see over here, these are the prompt, okay, that the software is making, and it is actually giving you the dimension by which it should have been. Here it says it is roughly around, if you cannot see it, 4.9194. Then you automatically know that it's not 4.9194. You can specify it to be 5 and then go ahead with the modeling part. So thereby all this information is available now. The last thing to do is actually compare it with the compare the scan body with the 3D printing body. Now what it does is that it creates a color distribution of what is the error between the model body and the 3D printed, 3D scan dots. Okay, so also it will try to investigate what are the features that are still missing in the body. Say this particular cut through, a toroid shaped cut through, okay, will be highlighted so that we end up making it. But the best part about this model is that we can change it while we are modeling it. Say there was a cut through profile like this, okay, and you don't want it to be a semicircular because you know there will be some production problem. So what you do is you create a square or a trapezoidal cut shape, okay, so that you can do it in real time. All right, and eventually this distribution of surface points in the object can be accumulated, and you can see where have you missed. So you can see very high accuracy over in these blue regions, okay, and a little low accuracy while as it moves across the height. This can be attributed to the fact that the projections which have been overlapped, actually when we rotated it, it could have been displaced also. Say for example, we have this cube, or rather an oblong shaped cube, for example, and if we had rotated about the z-axis, we should have made sure that it would not displace anywhere about the x and y axis. Okay, but that is very difficult to do, especially when you are dealing with a system with what 0.08 mm of resolution. Okay, that is really difficult to do. So thereby it sort of tells you that these are the problems in the sketch. If you want to handle it, not a problem. You can go ahead. If you want to ignore, that's all right. And eventually you can do a live transfer. So in this case, they are doing a live transfer to Creo and Proe. So in any way, you can do it to SolidWorks, you can do it to AutoCAD. So what it will do is, with dimensions and annotations, it will exactly transfer the part model, and where you can get the sketches, the part models, which can be edited for further printing process. Okay, so this was the part to which reverse engineering works. The further from it, as you would model and take it to print, slice it, then produce an STL file. Okay, these concepts come from henceforth. Okay, here till here you did the reverse engineering mode. Okay, now as you can quickly see, one of the most fascinating applications that I saw this time was the recreation of planet Earth from the GIS images. Okay, that was really fantastic. I saw it in a video. If I can, I'll share a link to it. Okay, so that's about uh, reverse engineering using scanning systems. Any questions about this?
Juan, I have a silly
Yeah,
question.
sure, sure, no problem.
Uh, how much time does it take to do this post-processing works in the software Geomagic Design X? Uh,
As much time as it would take to solid model it.
yes, that's my question was. Actually,
Yeah,
for a simple model like this, uh, this is as good as preparing the modeling the object directly in SolidWorks or AutoCAD, because it is
correct.
not that complex. So
Yeah.
for simple objects, do you suggest going for reverse engineering instead of directly developing it in 3D modeling software, or only for
Yeah, yeah,
complex objects?
right. Yeah. Actually, what happens is that the example that I have shown might not be the best fit. If one can recall from the previous lecture, uh, there was a bridge that was being 3D printed, if you remember, and it had multiple branches, right? So those system, can you imagine what sort of time that might go through to scan them, to replicate them, if one has lost the solid model? Things like this. This is the platform of the bridge. So in these cases where there's complex shapes and curves and things like that, even if you extrude, you will have to accurately design the spline that connects. Okay, this becomes really difficult. So the time taken to model this part by prompting and the time taken to model this part by prompting will be same. I hope you agree. Do you agree that the time taken to model these by prompting will be same?
Mm-hmm.
Right. So now you can see the difference. Then when you're modeling complex parts such as this that has been achieved through some topology optimization techniques, it becomes really easy to get this 3D scanning systems handy, and then apply it further in the production process. I hope that kind of clarifies the picture.
Yes.
But for simple model, it is not advised. Absolutely not. It's almost to a waste of time.
Yes.
And on top of it, you're not going to get the interior structures of the body.
And for
So
bar structures, if we
yeah,
3D scan it, so does it
yeah,
scale down? Means, is there any option to scale down it automatically? Suppose you were talking about the bridge or say a house, so you scan it, then is it, first of all, is it possible to scan a house or a bridge like that of that scale with
right. Just let me show you this. I hope. Yeah, this is C Cell website. Right. So this I'll share a link. So they did some scanning uh, of the entire region. So there's no page number to it, but you can check out refining post imagery by simple checking. Go to this
yes.
context, and then you can see how the entire building is
Three,
now
three, three,
recreated.
three buildings are there. Yeah.
Yeah, where it is recreated. Okay, actually, I should share the screen rather so that it gets convenient for everyone to check. Yeah. So these are the this is the system that is scanning, and Eventually, they are creating a map of each scan that is possible. So these buildings are being scanned, but through sort of a fish eye lens, and then the superimposition of the images takes place. So once these superimposing images are produced, the 3D structure of the entire, campus can be done. So if you take this system mobile, I believe that has no foundations to what can be scanned and then recreated. I would just like to add, actually, I was reading a very recent paper from a research lab in NTU Singapore, where the civil and the mechanical engineering people are collaborating to actually build robotic cranes. But the problem in building robotic cranes is that um, because they are exposed to the open environment, so there's no model to test them that if they'll work or not. So there's the huge requirement of actually recreating the spaces around. And now with the post-pandemic situation where labs have to be recreated, such sort of scanning technologies are much more relevant as they were 5 to 6 years back. So this is something that might interest people. What needs to be worked on is the algorithms that regenerate the surfaces. So I believe the software upgradation, the solid modeling has almost come to a saturation. There's not much more to add. One can model just about anything. But this part, there's a lot of research going on. So I can see Altair Corp and ANSYS, these are working to integrate such scan-based systems into their platform so that they can execute scan-based imaging altogether. Yeah. So anything else? Can
Glass.
you? Yeah, that's a very good question, actually. Yes, absolutely. You can scan glass-based structures. The thing is that you change the wavelength of light. You do not go for visible ranges, go for infrared, go for ultraviolet, and that way you can easily scan glass also. But this porosity has a certain backdrop to it. I forgot to mention. Good question. Yeah. Okay. Fine then. Maybe now what we can do is proceed further into the presentation. I should have actually put a blank slide in between. Yeah. So I hope the tomographic reconstruction was pretty eye-opening, as it was to me, because I only got to know about it recently. Uh, Here's another context which might be very, revolutionary. Okay. So, uh, how many of you have heard something called as the shape memory alloy? Have you heard about them? Anybody? Okay. Just a hint. What is it? I don't need a proper definition, but what's your notion about shape memory alloy?
I would say you can unmute directly and say.
Used in items such as braces. Okay, braces for teeth, if I'm right. I have not heard about the use. All right, never mind, not a problem. So what's a shape memory alloy? So what we do is we take, uh, just a second, I think this is the wrong presentation that I've opened. shape memory alloy. So in a nutshell, it is actually that if you have a certain structure, okay, so this structure will keep its shape if its chemical, mechanical, as well as thermal energies are in equilibrium, which means that if I interfere with the mechanical equilibrium, I bend the shaft, this shaft might change its shape. Okay. Then if I try to manipulate the chemical composition, the shaft might shrink or extend or contract. That could be also a scenario. And if I apply heat to it, that might melt. A section of the shaft might melt and the uh, thing will get distorted. So that's a very conventional thought process. But what if after you have removed these elements from the application, the shaft regains its shape back to its original form, right? Which means that the shaft remembers its original configuration, and therefore the term memory comes by. Okay, but it as happens so that not all materials tend to remember its original deformation, and by simply removing the external elements, you cannot regain the original shape, which means that once the shaft has melted, you cannot put it back together. So that's an entire different process. Chemically, if you change the composition while producing the shaft, you cannot alter the chemical composition. Mechanically, if you give it enough stress so that it plastically deforms, not elastically, plastically deforms, bringing back to its original shape will cause distortion throughout the structure. But there's something called as nickel titanium alloy that changes the shape upon the application of heat. Okay, and if you keep the heat applied, it will retain the shape. If you remove the heat, it goes back to its original position. Okay, so what can we conclude out of this? How is it anyway relevant to 3D printing process? Anybody? Anyone? What can we conclude from here? How can we use this in any 3D printing process? Any answers? Okay, no problem. So if I try to print this metal this time now, I can make an object which will get printed in one particular shape, but after cooling down, it will change its shape. Now, how is it of any importance? Say, for example, I am printing this L pin. Okay. By default, we know that if we go for an FDM process, we will require a lot of support structures, isn't it? Now, if I make this object out of a shape memory alloy, of which the memory is of a L shaped, okay, but upon application of heat, it undergoes a vertical transformation, which means that while I'm printing it, I can print it vertically, lay one layer upon each other, but as it cools down, it will slowly deflect and then come back to its original shape without any requirement of support. Okay, this particular process is called 4D printing. What is the fourth dimension here? It is time. That time is also a factor. Okay, Again, a very revolutionary concept is taking the whole engineering discipline by storm. So nickel titanium alloy, or popularly known as nitinol, okay, is a very famous alloy and one of the standards that the industry now uses for a very vital robotic application. Okay, we'll come to that a little later. But this is has extended the capacity of making micro electromechanical systems, or popularly known as MEMS. It is micro electro mechanical systems, which means that now what I can do is make very small robots or small devices that can go into your bloodstream with one chip, and then further, when it is induced with some, say, magnetic energy or heat energy, it will regain a different shape. So there is a medical application called stents, which are the most applied technology now. I'm sure some of you have heard about them because these are used in heart surgeries. Okay. Now the best part is that what you do is with a stent is you put down a stent in a heart. So if there's a blockage, it will go to that particular location and then extend the diameter of the vein through which now the blood flow can be in a regulated manner. Okay, so these are called stents, also made of nitinol, nickel titanium alloy, and these are the most, as I have already talked about, uh, I mean, industrially applied concepts from the shape memory alloy sector. So let's see what actually happens over here. As you can see, steel has different structures based upon steel has different structure based upon the temperature at which is at. Okay, so steel is nothing but a combination of iron and carbon. Again, if you manipulate the percentage of iron and carbon, the structure of steel changes. So you have something called you have something that ranges from cast iron to low carbon steel. Okay, these are the range. Also, the percentage of carbon is not very high. The maximum, I think, it is 6%, or in and around it, and the lowest being, of course, 0. I think 0.81%. All right, these are the compositions that form steel. Now, one of the structure is austenite. Okay, and a harder version of it is martensite. All right, as you can see, particularly the placement of titanium and nickel actually changes in a nitinol based cement, not cement, but alloy. Okay, so nickel metal is introduced in certain strategic places, and because of which the structure changes and it is more responsive to external environment now. Okay, so what's the highlight? It can recover apparent permanent strains. Strain is what? It is the, what is strain? I believe you should be able to answer this. Quick trivia. What is strain? Anyone? Okay, now I need to know if you are at all listening or not. What is strain?
So elongation, deformation in the length,
I cannot hear you, sorry.
deformation in the length,
Still it's unaudible. Okay, what is the unit of strain? Anyone?
Unitless.
Yeah, right. Strain is unitless quantity, which means that it is a ratio of something. What is that something?
So
It is the
change in
ratio of,
length by original length.
yeah, deformation by original length. Okay, that is strain. So it's going to undergo what? Permanent strain, which means that the state will be plastic and not elastic. In elastic, it comes back to its original shape upon the removal of external elements. Okay, so like I said, the shape memory alloys have two stable phases, a high temperature phase and a low temperature phase. Okay, the high temperature phase is a certain structure called the austenite, and the low temperature phase is called the martensite. So if you remember, as per temperature, the structure of steel change, and as per the application of heat, the two stable phases are austenite and martensite, even in case of nitinol alloy. Now, it is clear that even though there is a uh, these phases are stable, but they are significantly altered by dimensions. There is a evident strain in these two objects. Okay, so if you put them in a stress strain curve and based upon temperature, so this is a profile that you end up with. Okay, where something, a process called de-twinning. De-twinning is actually the displacement of molecular bonds. Okay, sorry, not crystal bonds that happen within a crystal structure, molecular bonds within a crystal structure. And de-twinning is the uh, the anti-process of it. Okay, you reorient the part from there. So as you change from a martensitic stage, you start applying temperature, it slowly goes to what? An austenitic stage. Okay, so it will bend, right? And eventually this whole curve can be plotted as you change the stress also, which means if you have put any mechanical stress in the system. Okay, right. So I have already mentioned that we can talk about, I wanted to talk about a significant invention that had been going around for this particular application. So can you identify what are these? Any guesses? Anyone? Have you ever heard
Robotic
of?
arms.
Yeah, exactly. These are for minimum invasive surgery. You must have seen them in Spider-Man, okay? Dr. Octopus, if I'm not wrong. So in minimum invasive surgery, you, instead of cutting open the torso of a patient, what you do is you make little holes. I think the standard norm now is to make 3 of them, and then you slowly pass these robotic arms. As they will pass, each section of this arm is actually made out of this nitinol alloy, and within it goes the heating elements, the control heating elements to each of the connections, and based upon that you can make the movement of the system. Okay, and this is the complexities of these structures can be now done with 3D printed nitinol systems. Okay, so moving on to the 4D printing concept, as you can see, it was printed this way, the Eiffel Tower, and as slowly the heat went out of the system, the Eiffel Tower was in erect position. So it can also be used or extended, the application of the systems, to something called as origami, where you take different shapes and try to make one single object. In this case, as you can see, a flower is being printed on a flat surface, but as the systems go down, I mean the heat goes out of the system, you end up with a spherical shape. Okay. Same goes for this particular structure, and these systems are actually used in robotics now for micro movements, and they are essentially used in navigation through very tight uh, spaces where cutting corners is not possible through wheel-based technology. Okay, so another application is when you are printing a composite, you can use our FDM technology for the same. Okay, and then you can load different layers, one of them which can be hydrophilic polyurethane core. Okay, and then based upon the amount of water that is present, these will contract and extend. All right. A very generic application of shape memory alloys is actually certain pipe attachments. Okay, in of course it doesn't happen over here, but in places where the winters and summers are extreme, so there's leakage due to expansion of pipe during the summer, and because there is a contraction of metal, okay, in winters, so these systems are now loaded with shape memory alloys which counteract the otherwise. Okay, now they will give a relative expansion because of heat, a relative contraction because of heat, and relative expansion because of cold, so which kind of balances the overall diameter of the system. How we can think about this is that when you are doing certain ultra cold, say 4 Kelvin experiments, at this temperature the shrinkage of metals is evident, but if you deploy some shape memory alloys which are tuned for certain contractions and displacement at this temperature, you can easily conduct the systems. Again, because in some cases the displacement and deformation rates are so small, these are often used to print electronic items, shape memory based actuators. Why? Because if you know, the Apple iPhone 10 has 1 billion ton transistors in its chip, which was the latest technology. I think it is at 4 nanometer scale. Okay, I'm not sure if it is 7. I think it is at 4 nanometer scale. So 1 billion in 1 square inch. You have to displace it by nanometers. So shape memory based actuators, which are 3D printed again, can be used to generate this sort of displacement. So that's a revolutionary idea, which is very current, very latest in 3D printing. I think this brings the end to the second part of the lecture. So we can, anything that you would want to discuss? Anything from the students? Any feedback? So think about something. Yeah, does the peeling step in SLA affect the shape? Peeling step. I'm not sure what's peeling step. Are you talking about thermal warping, Abhigyan?
Sir, like about when the platform moves up, then that process.
Yeah, actually, that's something that is not really in our favor. That is permanently distorting the shape. We cannot make it go back to the previous shape. Okay, so you have to identify which are the deformations that are advantageous to us and which are not. So this actually falls in the category of which are not, and hence we need to actually control the movement of Z stage such accurately that the as you call it, delamination of each layer does not take place. Yeah, good question. Anything? So now let me just give you some examples of what's with the 3D printing. Just give me 5 minutes. I'll go and get all the 3D printed parts that I have assembled, and I'll just come back in a moment. Okay, I just have to put everything on my table. Okay, so give me 5 minutes. I'll join back again in 5 minutes.
Okay,
Yeah.
sure. Okay, participants, so by then let's discuss about the site visit. And as already mentioned in the WhatsApp group, we will be visiting the know-how 3D printing lab on Tuesday. Okay, Tuesday is, I think, 9th. Yes, so on 9th of February, the time is tentatively fixed to be 10 a.m. So try to reach the Donna planet in ABC at exactly 10 o'clock, before 10 o'clock preferably. So we will assemble in front of the Donna planet by 10. Then the lab is like almost just 100 meters away from the building, Donna planet building. Alright, so let's assemble there. And for that, what I have decided that only the students who have submitted the assignment, okay, only they are allowed to join, because it is by default assumed that those who have submitted the assignment are the ones who are genuinely interested in this course. Okay, so I guess 29 or 30 are there, so 30 of you are welcome to come and visit the lab. And the resource person Ashish Baklewala, he should be there on that day. Even if he's not there, he has asked someone to guide you and show how printing are done. Alright, and regarding the model which was supposed to get selected for printing, I am still unable to decide, because all the drawings, all the models that you have submitted are very good. So maybe I will leave this judgment to Miss Amrita, your resource person for the SketchUp module on 31st of January, who took your class. So being an architect, I think she will be in a better position to judge which one was the best. So but anyway, all the models that you submitted are really good, and I hope you are able to gain some confidence during this entire process of this course. And after the end of this module, you will be retaining that skill with you, and I hope with proper practice, regular practice, time to time, you will come up with better realistic designs. Okay, it's not like that you have to do these things only when you have been given assignments or something like that. Even in your day-to-day life, you can like these things can be used. Okay, so maybe you can help your father to come up with a 3D model of your house, maybe for your neighbors. This for a small building of say 20 by 20 feet. Okay, 20 by 20 feet, it's a small building, maybe 1 or 2 rooms. Okay, let's call it a double-story building. That kind of building, when it is designed, that means all these 2D diagrams and the 3D house is modeled and handed over to the client, the money you can claim is near about 8 to 10,000 rupees. Imagine, just for a 1 or 2 roomed building. Okay, and for buildings like of a huge scale, say a normal residential building which 1500 square feet or 1600 square feet, for that kind of building you can easily claim more than 15,000 rupees. So these skills are not to be forgotten. You have to retain these skills. I am not only talking about buildings, for other things as well. The electrical engineers, as I said initially, they can use their skill to print circuitries. Today the research person was talking about the iPhone. So this all circuitries and everything, they can be printed. And the mechanical engineering students, this course is very relevant to you, as you might have guessed by now. So okay, we will not be having any closing session, so that's why I spoke out these things by now only. And hopefully we will have one more session, one more theory session, where one company called Nova Beans, okay, they are Gurgaon based company. They deal in SLA printers, so they may be taking 2-hour lecture on Tuesday, means after coming back from our site visit. Okay, so they have not given any written confirmation yet, but verbally I have spoken to them, and they have given a week kind of confirmation by now. So I will take that positively. So that will be your last class, and before that, in the morning half, we will be meeting near Dona Planet for the lab visit at 10 o'clock. Now regarding your certificates and other exams, what I said earlier is still same. Once you appear the NASCOM examination, Juan, are you there?
Yes, yeah.
Okay, can you, since you have already done one course in NASCOM,
Yeah.
so can you please tell them how this NASCOM organizes and what type of questions can be coming there?
Right. So I was the instructor of the NASCOM course on robotics, and apparently that was a huge course, pretty difficult for students to cope up. Actually, a 90-hour course, which means like almost 3 semester subjects, and they had a 2-hour examination at the end of the course, I believe, right after 1.5 months or so, and it was all objective based, but it was mostly graphic oriented. It was, the questions were not theoretical in nature, and robotics already has a lot of mathematics to it, and hence it was difficult for students to multiply matrices which are 4x4, but hence the expected output was actually not adhered. What you can expect in the NASCOM course is that it will be held online, and the other thing is, I guess you should prepare with a lot of pictures. Orientation, support, STL file, things like that. It will be entirely MCQ, so they will give you a section-wise report. And usually for robotics course, actually there was a very well-defined marks and margins. What was to come, what was not to come, things like that. I'm not sure if it is the same with 3D printing, but questions are on national level actually. A lot of students from NITs appear. I'm not sure about IITs, but I have found some NIT colleges going through NASCOM courses.
And how many exams they conduct?
Just one.
Not any midterm examination is.
Actually, I conducted the midterm examination. The faculty can opt for a midterm examination.
Okay.
I conducted a midterm examination, but it has no weightage to the final score actually.
All right. you are ready with the models.
Yes. So I'm just trying to find out the pictures of the 3D models that I was proposing. Just give me a moment. I need to find them so that it kind of gives a good relevance.
Okay.
Yeah, I have one now. Okay. Right. I hope the screen is visible. Okay. Right. So what you see here is that I hope almost everyone is familiar with a loom. A loom is a textile equipment which gives us the fabric from thread. All right. And a very elemental part of it is a shuttle. So as you can see, the picture on the right is of a shuttle, which is made out of wood, a single piece structure, and the center of it we plan to load a thread bundle, which will move to and fro and give us the necessary amount of thread. Okay. Now, what we were trying to do as a project is that we were trying to incorporate some metal blocks into the shuttle, which act as a magnetic device and thereby creating some motion. All right. But the problem was that the metal block, to support, we needed a very light weight in and around structures. And we came up with this model, as you can see on the left. Okay. Now we wanted certain features of the model. One, it had to be modular in nature. Okay. And two, because we were building this for the very first time, we might have to consider a lot of iterations as possible. Hence, 3D printing was readily considered. And we realized that we also have to keep in mind about the volume of the object. Since this is around 30 centimeters of length, we should be careful that we do not make parts which are beyond the capacity of the machine. So we decided to break it into several modules, and this is an exploded view right out from SolidWorks. So as you can see, over here are the symmetric structures. Okay, this one is symmetric. This forms one body. This thing forms one body, inside which pressure plate, cover plate, and this translator core, which is of metal, actually are made of one block and then fitted onto the system. So you can have n number of these and then fit them as per your requirement. Okay. So in that consideration, as you would see, we made some small holes and screws, okay, over here. And it would be soon realized that these are not only very difficult to manufacture, rather impossible. So firstly, we were wondering that if we make some projections out of them and we have a hole in between, perhaps because of the presence of the hole, we would end up, printing will be difficult in this case. So what we did is we removed the hole and we made some solid objects. But the problem is you cannot drill with 3D printed objects. Why? Because the melting temperature is around 200 degrees Celsius. So as you turn your drill into this system at very high RPM, of course you can do it in low RPM, what will happen is it will melt locally and you will get severe amount of deformations. Okay, so these are the considerations that one has to make while post-processing a 3D printed part. Then, because this entire assembly had to go into the system and remain fixed, we made some holes on the body, which was actually inclined at a certain angle. Okay, we used several printers for this, by the way, and we tried to superimpose one another and then come up with some different models. If that is it. Okay. So what I'll do is just, I believe the picture is clear. I'll turn on the camera. You can pin the screen, and then I'll show you the complete structure of the 3D printed object. Okay, do let me know if you can see it. Yeah, can you see this system? This 3D printed object?
Yes, it's visible.
Okay, so as you can see, these are of two different prints which go fit in one into another. All right, and this forms the entire part on which we can embed now the metal printing. So we have some holes over here where I have fitted some screws. Okay, all right, so this is one complete part, but the road to this was not that easy. I'll come back with some parts. These prints were done, by the way, at Know-How 3D. Okay, yeah. You can see these two parts also, which couple up and go. It has a little to no round edges, and they clamp into each other. The problem is that these projections, because of FDM 3D printing, as you can see, yeah, these projections, as you can see, are not fairly accurate to go into the holes. Okay, so if you start finishing them, it actually breaks, and this never made to the scene. Okay, this is prototype number 2. All right, now if you remember, I was talking about the heating problem, the warpage, thermal warpage. So we printed another one without a table that had heat. So can you see the bend of the material now? It is not straight as this. This is very straight, but this is not. I hope you can appreciate the same. Hope you can appreciate the problem. Okay, can you see the curvature? This is a thermal warpage problem. This part is now redundant. Yeah, any question?
No, sir, the bending is visible.
Yeah, right. So this is thermal warpage, and this is significant because why? I cannot use it anymore in my component just because it did not have a heating bed. Okay, some practical problems. Right. Then comes the one with multiple holes. Okay. Actually, I have a lot of junk now of 3D printed parts, but I have kept them because it's good if we study. So, problem with infill density. All right. As you can see, these are the frames, but can you see it's not entirely solid. They have holes in them. Okay. So when we began printing, the holes that needed to be made purposely were discontinued. Okay, they broke in between. So that's a breakage right there. All right, I hope you can see with the contrast. Yes. Okay, so this is one problem. The another problem is that if you have too many holes, like in the design, the delamination of the surfaces take place. You cannot make, if you do not have enough contact area for the layers to integrate, you will not be able to create the 3D printing parts as a whole. Okay, the most stable orientation was this, ground up, so it kind of started printing this way, but there was apparent breakage of the layers within. Not sure if you can see it. Is it focused? I don't think so. Right?
Yes, sir.
Yeah, so that's the problems with 3D printing. Okay, so this was all about the frame. What did we go through while we were fabricating smaller structures? So with a very low infill density, you will always have the problem of delamination. So as you can see, we had a very high fill density over here, but the interior of it was actually very light. This was the cover plate to the design. Okay, now you can see that the whole pattern is now broken down into smaller sections. Okay, so they go about printing these smaller sections once in a while, and then there is this small triangulation of the STL that you can see within the component. By the way, this was a failed component because of power disruption. So we could not complete it. Okay, so we went ahead and printed these parts also, okay, which are absolutely perfect, printed at know-how 3D, but I would still, not be very satisfied with the surface texture that was available at one end, of course, because these systems actually go for adaptive meshing, adaptive layering, slicing. So with adaptive slicing, what happens is that as you build upon the layers sequentially, you slowly and steadily, in the beginning, you go with a very high field density, and in the middle the least, and at the top the most, so that you get a very good outer surface finish. But the problem is, uh, if this adaptive slicing exposes certain parts of the system, it creates a lot of problem. These are all FDM printed parts. I did not show you the other SLA printed parts. So I'll switch on to actually another presentation, and there you can see the complete shuttle over it. Okay. Just a second. So the takeaways perhaps is that until and unless you print, you would not know actually what are the problems. We thought the model was perfect every time, but apparently some or the other problems was prominent and led to the failure of the proposed models. I cannot find the complete shuttle, but okay, never mind. I'll show the hard structure again. So as you can see, the shuttle had a conical front at the top. So we made this conical top, okay, this cone, all right, which had a hole in between, but this is completely solid. Okay, again FDM 3 printed, and you can see the staircase effect. Not sure, yeah, maybe here. You can see the staircase effect, pretty evident. Okay, yeah, right about there in the system. We went ahead and modified with the SLA, and we got this and rather carved out lightweight 3D printed part. Okay. Upon operation, it was evident that we were facing problem with certain breakage when we are operating in the machine. Can you see how it broke down? Okay, right over here. All right, so we had to go ahead and design it at a greater thickness, and that was only when it was known. So a lot of design iterations, and finally we had our complete shuttle, which is now assembled. Now this shuttle that we have designed also has bearings, metal bearings within the periphery. Okay, I'll maybe over here you can see. Can you see the metal core? This is the metal core, and this is the entire shuttle now with conical parts. Now with SLA based 3D printing, you will see a lot of surface aberrations. Why? Because it is exactly where the supports were put down. Okay, so this is all done in AC with the SLA printer, and you can see here, over here, there are small metal bearings, okay, inside of them. All right, and they are assembled by a shaft in between and are kept hold very rigidly, very firmly. Even if I try to pull it apart, it won't come off. Okay, so this was the last prototype, and after quite a bit of iterations, we came up to this particular model. So because of 3D printing, perhaps I can now convince you that iterations, large amount of them, is actually possible through this system. And by the way, this was printed in one single hole, go, which is like we did not break the assembly. We made the assembly and then put it to print, and it printed out accordingly. It took about 6-7 hours. The problem with SL is that it needs post processing. It has to be cleaned by ethanol first, so that all the inhibitors are removed, and then followed by as you call it, UV curing. Yes. So what happens is that right after printing, this parts, SLA based parts, are pretty soft on touch. So we'll get a lot of surface deformity if you don't hard cure it. So they go to a UV chamber and then cure the parts as it is, and thereby giving you perfect tolerant products. So the finish level in this particular system is around 120 microns. Okay, whereas in FDM it was roughly around 1000 microns or something like that. Okay, so it's pretty, I mean, order of 10, right? So that's my experience with 3D printing, and I shared as much as I know about 3D printing. So any questions related to this? Yeah, Vibhuti, is it in the syllabus, the G code exam?
Syllabus, it's not directly written these things. So whatever is in the module, na, I shared one schedule with you, right?
Yes.
So
Yes.
Students, whatever is in the schedule, only those things are written as syllabus. So we also actually don't know what is coming in the exam and what is not coming. So we have one group of the trainers who are trained in 3D printing. So we will discuss, and maybe we will come up with some sample questions. And Juan, also you may provide some materials to read. So where
Sure.
all these things are written.
Right.
Okay.
I'll share. Oh, I think there is a set of sample questions in the NASCOM website.
Actually, when you said na, I tried to surf their website and look into these questions, but it was not available directly. I talked with Kamini. Kamini told that NASCOM actually generally mails those questions, sample questions. So if you somehow get the link of that website, where it's available?
Oh no, I actually had it. Let me check. I had it with me because for robotics I got it. I
Okay.
got some sample questions for robotics. I did not check for 3D printing though.
No, so you got it through mail or you got it in some website?
No, actually I got it through. I think I got it through. I believe it was available on the website itself. I checked the website, and then I got it. Still, let me just.
Okay.
I mailed actually to some people. I'll if it is available, I'll share it with you.
Okay, that will be great. So if nobody has any question, then Juan, we would like to take one, photograph screenshot with all the
Okay.
cameras on of all the participants. And I am facing one problem. I don't get the tiled view of the participants. So may I request Syamali, are you there?
Yes, sir.
So do you know how to get tiled view of all the participants?
Yes, sir.
Okay, so participants, can you please turn on your camera, including Syamali and Juan?
Yeah. Right away. Oh, okay. I have to. I think. Yeah. That's great. Oh, I can see a lot of people already engaged.
Agyan, Akash, Maitri, Rishikesh Medhi. No, I think they left. But anyway, Shyamali, did you get the picture?
Yes, sir.
Okay, okay then. Thank you.
Thanks a lot.
Yes, Juan. Thanks a lot from my side. And
Thank you, sir.
participants, they didn't open up much, but still, thanks a lot from on their behalf as well, because they will be knowing the benefits of these lectures because they are recorded. So
Right.
in future, if they need any kind of reference, they can easily come back and refer to this lectures taken by you. So
Yeah.
thank you, thank you again.
Thank you to all the participants at the foremost, because uh, I'm sure 2 hours is quite a long time, and it's very difficult to sit down patiently, listen to some very thought-provoking concepts which are not directly related to the academics. So thanks a lot for making the time out for yourself. I hope this helps, if not at all, but a little marginally. Okay, so a big thank you to Bibhuti sir and his dedication in taking this NASCOM course. So I would like to close here, thanking you again. If you have any queries, do write to me. Uh, Even if you are looking for internships and anything at IIT Bombay, please do write to me. I can forward it to some people of your discipline. Okay.
Thank you, Juan. Thanks a lot.
All right. Okay.
Okay.
Thank you, sir.
Yes.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.